Hello everyone, my name is Pedram and I'm a professor in data analytics. Welcome to another episode of Deep Learning. This is part 3 of module 6, Deep Sequence Modeling, Natural Language Processing. In part 1, we talked about sequence modeling design criteria. Specifically, we mentioned that there are 4 things that we need to have. 1, the architecture should preserve the order. 2, can handle different input length. 3, it better share parameters across the sequence, and 4, it should account for long-term dependency. Then we talked about the simple recurrent neural network architecture, which was able to address almost all of those criteria except the last one, which was the long-term dependency. That's why we said we have to go beyond RNN, and we introduced the idea of gated cells. And we talked about LSTM architecture, long short-term memory, in part 2. We talked about different gates, we covered the mathematics behind it, and we use these models, both RNN and LSTM, for time series. In this video, in part 3, we want to talk about how we can apply these models into text. So this is the natural language processing section. Part 3, deep sequence modeling for text, natural language processing, NLP. All right, let me quickly remind you of different kinds of sequence data that you already talked about in part 1. We said that we can have time series data, we can have text data, we can have audio data, and video data. These are all examples of sequence data that we can handle with this architecture, this recurrent neural network architecture. So in part 1 and 2, we covered some examples from time series data. Now we're going to talk about text data. A quick reminder of different RNN architectures and applications that you should be quite familiar with at this point. So we can have many-to-one architecture. So for example, we have a sentence or paragraph, and then we pass it to the model, and the output is going to be, okay, the sentiment is positive or negative, right? So this is many-to-one. We can have one-to-many. So the example is that you can pass an image to remember, image is a sequence data as well. We can pass it to the model, and the network is going to generate a sequence of output, right? So for example, we can say a train traveling down a track next to a forest. We can have many-to-many aligned, many-to-many not aligned. So example for the many-to-many aligned can be, music sheet generation. You have the notes, and the next note is going to be predicted, and etc. We can use many-to-many aligned for machine translation as well, but it comes with the restrictions that the number of words that you input the model is going to be equal the number of words that the model is outputting. If you want to be more flexible in translation, we can do many-to-many not aligned, right? So here we pass the entire sentence to the network, and the network is going to generate something else. And again, this does not necessarily need to be at the same length. All right. Okay, now let's see what is this natural language and why do we call it natural? So human language versus machine language. In computer science, we refer to human language as natural language because it is shaped by an evolution process, just like any biological organisms that we have, right? So that's where the name natural is coming from, because it happened naturally. And however, machine language is designed for machines, like low-level programming languages like XML, assembly, and etc. Right? So here is at the very high level how machine language is different from human language, and this is the case as of today, right? So these things, especially for the machine language side, might change. No, actually, will change, or it's just a matter of time. So for example, we can look at complexity, creativity, ambiguity, learning, and adaptability, right? So of course, human language is a lot more complex, right? It is a lot more ambiguous, and it can be well, at the same time, it can be very creative. So these are the strength of human language, and the way that it's learned, it's basically naturally. As I said, usage comes first, and then the rules come later. So it is acquired naturally. And adaptability, it's highly adaptable. However, on the other end, machine language, of course, it is structured and logical with limited creativity, and because it's structured, there is little to no ambiguity, of course. And however, the learning process is that it should be taught through programming, and because of that, it is kind of fixed and rigid. So again, just keep in mind, this is the case, especially for machine language as of today. So things are going to change for sure in the future. All right, so natural language processing, what is it? As I said earlier, because human language is complex and ambiguous, making sense of this human language through a bunch of algorithm is a big deal and it's difficult, right? And NLP is basically it's there to make that happen. So NLP is a subfield of computer science and AI that deals with this interaction between computers from one side and human language on the other side. And however, again, this is a difficult task. And traditionally, back in 1960s, the traditional NLP started with finding basically handcrafted rules, right? So like it was like something like this. Okay, here's a rule set for English language, right? And these are the grammars, these are the syntax, and now go ahead and understand human language, right? So the goal was to understanding by going over those handcrafted rules, understanding the human language. So as you can guess, this is a lofty goal. So the modern NLP is doing it differently. So in modern NLP, it's all about using machine learning to automate the search for these rules, right? So we're not going to handcraft those rules. We're going to come up with some algorithms and machine learning techniques to automate that search for the rules. And of course, we're going to enable computers to do some cool tasks. So just to reiterate again, in modern NLP, the goal is not to understand the language. The goal is to just ingest a piece of language as input to the model and return something useful. And those useful things can be something like this. So for example, does this text has a positive or negative sentiment? This is your sentiment analysis, right? How we can translate this text from English to French? This is your machine translation. Does this Twitter, I don't know, has it basically contain abuse or not? So this is your content filtering. And for example, what's the topic of this text? This can be your text classification and many other useful applications that we can nowadays use with NLP, natural language processing. So just to reiterate, the goal in NLP is to automate this pattern recognition. What is a pattern at the end of the day? It's basically statistical regularities. The goal is to find those statistical relationship from the data. This should be quite familiar. We have seen this thing in computer vision as well. Actually, indeed, in computer vision, we said that the pattern recognition is applied to pixels. We wanted to come up with these high-level features at the end of the day that can basically represent the data, the pattern in the data, right? NLP is pattern recognition applied to text. So this is a difference between maybe computer vision and NLP. Again, the goal is to learn these patterns, these high-level features, and then pass it to a machine learning model and then make a prediction, right? So NLP is pattern recognition applied to text like words, sentences, and paragraphs. What are the tool sets? So not so long ago, our very basic machine learning models like decision trees and logistic regression were considered the state of the art when it comes to NLP. And we're talking about 1990 to 2010. Again, this is not too long ago. And then after that, the recurrent neural networks completely take over between 2010 and 17. Models like RNN and LSTM basically completely outperform the classical machine learning models. And for example, bidirectional LSTM was considered the state of the art for a couple of years and was performing very well for NLP problems, right? But now we know that after 2017 and 18, with that paper, that attention is all you need, and the transformer came into place and they took over everything. Actually, transformers became so successful in short amount of time that they kind of revolutionized everything when it comes to NLP. And now we are going to use it for computer vision, for natural language processing, for actually any kind of deep learning models. Transformers are applicable. So that's this is the goal and tool set for the NLP. Now let's look into the steps that how we prepare data, how we prepare text data to pass it to an NLP model. Okay, let's talk about preparing the input data for our natural language processing model. So there's this thing called text vectorization, and that's the process of transforming text into numeric values, right? If we can transform the text, the input values into numeric values, we're done, right, in terms of modeling, because there's nothing new. We have already seen recurrent neural network. We are familiar with the architecture of LSTM, gated cells, and GRUs. So we already know the architecture. So if we just transform the input from text to numbers, we're done. So let's see what are the steps in this transformation. There are 4 steps. Now, the first one is standardization, then tokenization, indexing, and encoding. So here at the very at a very high level, this is what we mean by all these 4 steps. So imagine this is a text. The cat sat on the mat, right? So this is your original text. First step, we have to standardize things. There are different methods for standardization. The common ones are, for example, we remove the punctuations and we convert all the words to lowercase, right? So for example, we're going to remove this punctuation. We're going to make sure that all of them are lowercase. So this is the standardization, right? Then in the next step, we need to tokenize these sentences, right? So tokenization basically is breaking down your sentence into small pieces. We are going to call them tokens. And again, there are different ways. We're going to look into them later. There are different ways for tokenization, but let's say this is the way that we do it. No, the cat sat on the mat, and we're going to break them into one single word, right? Then the next step is indexing. We're going to assign a number to these tokens. So imagine these are the numbers. And finally, we're going to encode these numbers. There are different ways of encoding, one-hot encoding, multi-hot encoding, and etc. So let's look into the details of all these 4 steps. Starting with standardization. This is step number 1, right? So we are here, we have a text, for example, the cat sat on the mat, right? What are different ways that we can standardize a text? So these are the most common ones, especially the first 2. Converting to lowercase, make sure that all the letters are lowercase, and then removing punctuation. So these are the ones that usually it's built in any kind of text vectorization layer that you're using in TensorFlow, right? Okay, so the punctuations can be exclamation, dots, question mark, and etc. Right? Then the next one is converting special characters. So for example, we have this accent grave, I don't know, for example, in a word like Mexico, there is this accent grave. You can get rid of this one, or you can get rid of different other special characters and just replace it with the simpler one, right? And the next one, which is also important, is called stemming, right? It's basically, we want to go back to stems, go back to rooms, right? And the idea is that to convert variations of a term into a single shared representation. So for example, we have a word play, and in the text, we can have different versions of play, right? We can have play, plays, we can have played, we can have things like that, right? So these are all different variations of the same word. So we're going to replace all of them and use one word, right? And the word is play. So that's the stemming part. So as you can see, standardization is a basic form of feature engineering. So this is, and it's going to be done. Of course, we're going to pass these methods to the layer, and it's going to be done automatically. So this is a kind of feature engineering. And also know that with standardization, the model requires less training data. So obviously, for example, here, instead of training the model on 3, 4, 5 new words, we're going to use one word. So that way it's going to generalize better. So this is a plus side. And however, we should be very careful that this standardization may sometimes remove some useful information as well, right? So for example, question mark. Imagine the task is, distinguishing if a text is a question or answer. So if that's the case, now question mark should be treated as a special character instead of being dropped out, right? So these are the different ways that we can standardize a text. So we go from this to standardized version. Okay, step number 2, tokenization. So tokenization is basically the idea of splitting text into units. We call them tokens, right? So we are here now. So we standardize the text now with the cat sat on the mat, and we can tokenize it, right? So there are different. Let's see what are the different ways of tokenization. The first one is word level tokenization, right? So this is, we're gonna we call it space separated tokens, right? Because if there's a space here, we can basically separate them, right? So this is what we did in the previous example. So we use the word level tokenization. So now that sentence is going to become the cat sat on the mat, right? So this is word tokenization. We can do n-gram tokenization. So n-gram basically means a group of n or fewer consecutive words put together. So we do it basically synthetically. We want to make sure that there's this local ordering that we are incorporating with n-gram. Let me tell you what I mean by that. So imagine n is equal to 2. We call it bigram tokenization. And we're working with groups of words that has length 2, two words or less, right? So this, for example, this is going to become something like this. It's set of word like the, then the cat. Again, remember, two or less, right? Then we have cat, we have cat mat, or cat sat, sorry, cat sat. Then we have sat, hopefully it makes sense. Then we have sat on, right? So a group of two words or less for the bigram tokenization. Then again, the goal is to, if you do, let's say, n is equal to 3 or n is equal to 2, the goal is to reserve this local ordering, right? So for example, cat, sat are coming after each other. So we want to keep that. And the last one, that last method for tokenization is character level, right? So this is character level tokenization, and as the name suggests, each character has got its own token. So for example, if I want to use character level tokenization here for the sentences, the is going to become T, H, E, and then we have cat. You get the idea, right? So we have cat, C, A, T, and etc. Okay, so character level tokenization is basically it's rarely used in practice. However, for some special cases like text generations and speech recognitions, of course, character level is used, right? So this, for example, the chat GPT uses character level tokenization, means that the model breaks down the input text into individual characters rather than words or n-grams, right? So this approach is going to allow the model to handle a wide variety of languages and input formats without depending and relying on predefined word lists or language-specific rules, right? So basically, it means that it enables the model to capture some important information about spelling, punctuation, and maybe other linguistic features that might be lost with a word level or n-gram approach, right? So for example, if you've tried ChatGPT, which I bet you have done, you can see in different other different languages, you know, you can try Chinese, French, German, you name it, and the text, the output is going to be generated word by word because it has been the model, the input of the model was character level. Okay, in general, there are, so this is important, I want you to pay attention. There are two kinds of text processing models, right? We can process a text as a bag of words or as a sequence model. So what is a bag of word model? So bag of word model basically is going to treat input words as a set, right? So that means that it's going to discard ordinal ordering. So, and for bag of words, we're going to do n-gram tokenization. So let me tell you what I mean. So imagine I'm looking at these tokens. If I want to treat it as a bag of words, it really doesn't matter how I mix these words. If I'm doing, let's say, word level tokenization, the cat sat on the mat, it can be anything. It can be mat, sat, on, cat, and I can mix this, right? The ordering doesn't matter. However, if you want to inject some sort of local ordering, you're going to do, for example, bigram tokenization, or n is equal to 3 or n is equal to 4, right? So this is, as you can guess, this is kind of feature engineering as well. So we can go ahead and play around with this number n and see which one is going to do a better job. But just remember, if you're treating word as a bag of words, so basically you have a set of words and that's it. So you're discarding the original order, right? On the other hand, we can have sequence models. So in sequence models, of course, word order matter. So it means that if you have tokens like the cat sat on the mat, it comes at the same order, right? So we usually do word level tokenization and we keep the order. So the order must be preserved. All right, so these are two kinds of text processing models, bag of words and sequence models. Okay, the next step number 3, is indexing. So we standardize the text, we tokenize it. Now it's time to assign some numerical values into that, right? So that's basically indexing is assigning an integer to each of your tokens, right? So for example, we assign number 3, cat 26, and etc. And as you can see, there's another number 3. Okay, so this is the indexing. And usually we restrict this vocabulary to the top 20,000 or 30,000 most common words, and basically to keep the feature space, manageable, right? Because Indexing those rare terms would result in excessively large feature space, and most of the features would have almost no information content, right? So we're going to restrict it to 20,000. 20,000 usually works, or 30,000 if you want to be more restrict, right? There are two integers that are reserved, two indexes that are reserved. One is index number 1. It is reserved for, we call it OOV, out of vocabulary. So this is OOV token. And index number 0 is reserved, we call it mask token. It's for, basically it means just ignore this one, and just, this is used for padding. So for example, if we have a sentence like, I don't know, my name is Pedram. Obviously, Pedram is not going to be among the first 20,000 common words in English. So it's going to give you, and imagine we are doing word level. Yeah, let's do word level tokenization. It's gonna output something like this. I don't know. I'm making up these numbers. No, maybe my is, I don't know, 65. Name is 20 something. Is something. I don't know. And then for this one, which is not there, it's gonna show you something like this, unknown, right? So usually it's UNK. So this is basically unknown. And the index is going to be 1. So index is going to be 1 when we are going to convert back this integers to words. This 1 is going to become UNK, unknown. Okay, the last step, which happens to be a very important one, is called encoding, right? So we standardize the text, we tokenize it, we convert it to integers, these are indexing, and then the last one, encoding. So there are different ways of encoding. The first one is multihot, or we call it binary encoding. It encodes the tokens as a multihot binary vector. So for example, we have something like this. And remember, our vocabulary size, let's say vocab size was 20,000. Then we're going to say that let's put this vector, let's put these numbers into one vector. So this is important. The size of this vector is 20,000. And wherever that term showed up, so for example, I don't know, it was number 3. So you put a 1 there, otherwise it's 0, right? So it's going to be very, a vector like this. So the cat sat on the mat is going to become something like this at the end of the day, right? So again, here we're going to have 20,000, almost all of them 0, except 5, 6 of them, 1, 2, 3, 4, 5 of them are going to be 1, right? So this is called multi-hot or binary encoding. Okay, the next one is one-hot encoding. So we're going to say, okay, let's take these numbers, right, change into 1 and 0 and 1s, right? So this is going to be super high dimensional, right, because we have 20,000 features now. So every vocabulary, I'm going to call it vocabulary 1, text, let me call it word 1, or whatever, word 1, word 2, we have 20,000 of them. And then we are going to come up with this 20,000 vectors, right? So this is one-hot encoded. So as you can see, obviously a downside of one-hot encoding is that it's going to be, the dimension is going to equal to the dimension of your vocabulary, which is not necessarily ideal, right? So again, there's going to be zeros, and then for the word that appears, there's a 1, and everything is going to be 0. Okay, so this is one-hot encoding. And the other one is called TF-IDF. So it stands for term frequency and inverse document frequency. Let's look into that. Let me actually tell you one more thing before I go to the TF-IDF. So as you can see in this example, for example, the cat sat on the mat, the word "the" is appearing twice. So maybe you want to count for that, right? So if you want to count for that, there is another encoding method called count. So let me, maybe I should have added it here. So this is count encoding. And we don't do that because we can do TF-IDF. It's a different version of count encoding, but it's incorporating the number of times that these terms are showing. So simple, the plain version of count encoding is that go ahead and assign one extra number to each word, right? So for example, if the word "the" is appearing twice, so we know that we have "the," which is appearing twice. So let's put a count 2, right? But this is not necessarily ideal because it's gonna if a term is very, very frequently used in a context, so we're going to have a very large number for this, and we have to standardize it, and etc. There's a better way of doing that, which is TF-IDF. So let's look into what is TF-IDF. I'm going to go ahead and erase these things because I want to show you an example of what is TF-IDF. Okay, let's actually, it should be fine. All right. Okay, imagine we have a text classification problem, right? So we have, let me actually write it down because it is important. There's this document. It can be your paragraph or set of a bunch of words, right? Versus data set. This is your entire data set, right? And imagine you have a bunch of documents, right? So documents, it's one paragraph, two paragraph, whatever, right? And you want to say, okay, this document is, I don't know, finance related. This document is marketing. This document is anthropology, right? This is, you want to classify them. Let's say there are these three classes and there's another class, machine learning. And of course, these are not the best examples, but they get the idea, right? So these are each documents, and the dataset has so many of these documents, right? Now we want to count the number of times that each term has showed up in two of these things, right? So I need to count. So for example, if I see the term machine learning in a document, so it means it's important. I need to give it more weights, right? To make sure that that machine learning is basically having more weights here, and it's important for classifying this document in the entire data set to machine learning, right? On the other hand, the number of times that that term is showing up in the dataset as well also matters. So for example, let's say we have the word the. Of course, if I look at the entire dataset, and this term is going to be repeated a lot in the dataset. So we have to normalize this frequency by the number of times it's shown up in the entire dataset, right? So so this is, roughly speaking, we have something like this. The TF-IDF is capturing something like this, roughly. So in the numerator, it's going to be the number of times. So I can say count the number of times that that term is showing up in the document, right? So let's do Python language, for example. I call it document.count, and your term. This is your special word, and you want to see, you want to divide it, you want to basically normalize it by the number of times that this term has been shown in the entire data set, right? So here you have a for loop, for example. You're going to put a for loop, and then you're going to go over the doc.count terms in the entire data set, right? In the entire data set. So basically, this means that, okay, if in the document this thing was repeated 10 times, but in the entire data set it's very prevalent, right? It's very common. So it's not going to give it enough weight, right? However, if you have a term that in the document it was, in the document it was repeated, I don't know, maybe 15 times, and the entire data set was only repeated 30 times. Again, this is going to be a weighted version. It's not exactly, don't do 15 divided by 30. We're going to work with the standard version of that. But the point is that it's going to give this word more weight. TF-IDF is going to give this word more weight compared to this word, and that's going to help for classification. All right, so these are the steps of text vectorization, standardization, tokenization, indexing, and encoding. All right, before we go to the modeling section, I want to talk about one last subject which is important you should know. It's called word embedding. So what is word embedding? Remember, the encoding thing that we did in the previous step was, we do one-hot encoding, multi-hot encoding, and TF-IDF. These are all hard-coded, feature-engineered encoding, right? So what if the idea is that what if you want to learn those encodings from the data, right? So that's where word embedding is coming from. And here, for example, I'm going to show you one-hot encoding. This is a one-hot word vector versus a word embedding, right? So as you can see, one-hot, of course, is sparse. There are maybe a bunch of ones, and then the rest is all zero, right? And then it's very high dimensional. Remember, if your vocabulary has a size of 20,000 or 30,000, it's going to be, dimension is 20,000. 30,000, and it's hard-coded. The idea of word embedding is that these are dense, lower dimensional, and structured representations of the words learned from the data. So this is key. They're learned from the data, right? So at the end of the day, word embedding is going to give you a bunch of basically features, typically thousands of those features that are interpretable, and they're potentially useful. So what do I mean by that? So for example, we end up with, let's say, we end up with a vector or word embedding vector called, I don't know, gender, right? This is gender. We can have gender vector, we can have plural vector, we can have verb tense vector. So this means that if I have this vector, if I have this representation, now if I pass it to, we know that there's this vector is the relationship between male and female, right? If I apply this vector to man, I will automatically get the word woman. If I apply it to king, I will automatically get the word queen, or the other way around, right? So this is going to be very useful. The same story for verb tenses, right? So for example, there's a vector that's just translating walking to walked, or swimming to swam, right? So this is a past tense, right? And another example is going to be country capital, right? So here, for example, Canada is going to be passed to Ottawa and etc., right? Spain, Madrid, and etc., right? So we can come up with thousands of these features which are basically interpretable, and of course the dimension is going to be a lot lower compared to one-hot encoding, and these are dense structured features learned from the data. So this is the concept of word embedding. I'll talk about the word embedding more by the end of this lecture when we go over the concepts of transfer learning in NLP. Okay, now let's go to the modeling section. Okay, for the modeling, depending on how we represent groups of words, we can come up with two types of modeling. One is bag of word approach, the other one is sequential modeling approach. I think this table is going to help you understand the difference between the two. So for the bag of word approach, the input basically is a collection of text documents, right? So it's a set of words. This is the input. In sequential modeling, the input is a sequence of words. So as you can see right away, the ordering matters in the sequential approach. So this is the second one which I highlight. Let me use another color, maybe orange. The second one that I highlight here, order. The bag of words is going to ignore the order of the words, right? However, the sequential model is going to capture that. So here, bag of words, when we say it ignores, remember, we are using n-gram tokenization, right? If I do bigram tokenization, or n is equal to 3, we are somehow artificially injecting that local ordering, but obviously we're not looking at we're not aware of the entire context, right? So or maybe for a longer sentence. So just when we say that it ignores the order of words, remember it ignores the order of words for longer sentences. And if you're talking about local ordering, like n is equal to 2 or 3, we can do n-grams, and it will incorporate those short space orders, right? Context-wise, because again, the bag of words is going to ignore the context of a word, because that's the nature of it. A sequential model is going to capture that because it's preserved that ordering. In terms of features, in bag of words, each word is a feature. In sequential modeling, the number of features depends on the model architecture. So for example, we can do word embedding and use number of features 128. We can do 256, right? So these are, we're going to, depending on what architecture you want to use, you can specify those numbers. So obviously the bag of words is going to be a lot more high dimensional compared to lower to sequential model, because again, you can use word embedding with only 128 features. Sparsity, bag of words is going to be highly sparse. Sequential modeling has lower sparsity, and because of that, because it has high sparsity, the bag of words, it's going to be faster, right? There are going to be lots of zeros and ones, and then this is easier for computer to calculate. So it has faster training and inference, bag of words, compared to sequential model, which has a slower training and inference. And finally, in terms of suitability, it all depends on the context, right? What kind of problems you're dealing with. Usually bag of words is good for simple tasks like document classification, and sequence modeling is good for more complex tasks like language modeling and machine translation. And also the task that the ordering really matters. So for example, you are doing sentiment analysis, right? And then you have two words, two sentences. No, you can say the movie was good, not bad at all, or you can say the movie was bad, not good at all. So as you can see, we're using exact same words, but the ordering matters a lot, right? You can argue that, okay, I can do, for example, 3 gram n-gram bag of words tokenization. It's going to do the job. The answer is yes. So for that reason, usually when it comes to the basically task like simple document classification, you want to say if a document is a finance, is a machine learning, is it marketing, whatever, and then you can, it really, the ordering doesn't matter that much, especially if you're using TF-IDF or things like that. No, you can control for those kind of things. However, so this is for language, right? Natural language. natural language processing, we can do two ways of modeling. However, if it is time series, then we cannot do this kind of approach, right? It doesn't make any sense. For time series, we have to always do sequential modeling approach. So for example, I don't know, we looked at an example in the previous part, and we were looking at the weather temperature. There's no way we can mix that data, right? So we have to preserve the order. All right. All right, now let's look at a simple example and just be aware that we are going to apply both the bag of word approach and sequence modeling approach. Just be aware, historically, this field, the natural language processing, is started with the, let me use the right color, with the bag of word approach. And then after 2015 and 16, when RNN and LSTM became a thing, we started using the sequence modeling. And today, both of them are relevant. So both the bag of words and sequence modeling are relevant, and we can apply both of them and see which one is performing better for our problem. So here's a simple example. The dataset is a famous one. It's called IMDB movie review, and the task is to basically classify. This is a sentiment classification, right? You want to see if the review on a movie was a positive or negative thing. Okay, so let's look into that example. Okay, let's start with a very simple bag of word approach. Okay, here's the TensorFlow code. Don't worry, we're going to review these things in the Python section of the course, but I just wanted to highlight how we can do it at a very high level. So we're going to start with the simplest version of bag of words, which is single word. We call it Unigram tokenization with binary encoding, or we also call it multi-hot encoding, right? So what does that mean? It means that we can represent, let me actually show all of them. We can represent the entire text as a single vector. So there is this text vectorization layer that we have to start with from there. So here on the right, we have max tokens. These are 20,000. So basically means that our vocabulary size is 20K, 20,000, and we are doing multi-hot encoding, right? So this means that because I'm doing Unigram tokenization, a sentence like this, the cat sat on the mat, is going to become, every single word, it's going to become something like this: the mat sat on the. And as you can see, it's a set of words. There is no ordering there, right? It can be, it can come as any order. So it's basically a set of words. So this is our Unigram. Multi-hot encoding is going to make it something like this. This is a vector of dimension 20K, and we have a bunch of 0, 1s, right? So the entire text is a single vector now. So after this vectorization, we're going to pass it to our model. So I'm going to take this, pass it to the input, and as you can see, max tokens at 20,000. We're going to use 16 nodes. Let me talk about it why. And then here the input shape is 20,000, right? It's a tensor rank 1, right? So because this is, remember guys, this is a Unigram and this is bag of word approach, there is no ordering. We don't need to do RNN or LSTM. We're going to use simple dense layer, right? So this is exactly what we're doing here. Let me actually highlight it. So here we're going to use a simple dense layer. No LSTM, no RNN, again, because there's no ordering. We don't do sequential modeling. So we use a simple dense layer with 16 hidden nodes, activation ReLU, and then we are going to add dropout after that, just for regularization. Finally, we're going to add our output layer, which is 1 unit, and activation function is sigmoid. Again, we are doing classification, right? Either sentiment positive or negative. And I think the rest is pretty straightforward. Just remember the loss function is binary cross entropy, and we're going to track the accuracy. Okay, so what is the output of this very simple bag of word model? Naive baseline, let me actually use pen. Naive baseline performance is 50%. This is the accuracy, right? The data set is balanced. Your benchmark is just flipping a coin, so it's 50%. Then with this model, we can get the test accuracy to 89.2%. Not bad at all, right? So let's see if we can improve that, right? So one thought that you can have, in order to improve this, you might say that, okay, you know what? Maybe this Unigram is too much, right? Maybe I should look at least some local ordering. Let's go from Unigram to Bigram, and this is what we do next. Okay, so here's our second model. We started with a Unigram with binary encoding. Now let's do Bigram with binary encoding or multi-hot encoding. So basically the idea is that we want to add local order information. So a sentence like this, the cat sat on the mat, is going to become, remember, binary or bigrams is using n is equal to 2 or fewer. So we have 1 or 2, right? So the cat, sat on, and on the mat and mat. So this is how what is the output of the bigrams if you pass it this. This is the way that we tokenize it, right? Now, if we do it this way, because we are adding some local order information, then the accuracy is increasing actually. So again, our text vectorization layer is like this. We are going to do n grams is equal to 2, the same number of vocabulary, 20K, and the same output mode, which is multi-hot encoding. Okay, so naive base 50%, Unigram binary 89.2%, Bigram binary 90.4. So this is good. This is not bad at all. Let's see if we can do even better. Okay, we like the Bigram tokenization method, so we're going to keep into that. But we're going to change our encoding method. We're going to use TF-IDF. The idea is that, so this is term frequency, inverse document frequency. The idea is that let's see those reviews that we have, the number of terms that the number of times that each term is basically repeated in each review, compared to the number of times that term is repeated in the entire data set, has something to do with better classification, right? So we want, if we weight those words differently, if you get a better thing or not, right? Typically, if you do TF-IDF, it should increase the performance model by 1% in the test set. And however, here it wasn't the case, right? For the IMDB review data set, it wasn't the case. So in terms of text vectorization layer, so again, n grams, we are using the bigrams, 20,000 tokens, and now the encoding is TF-IDF. So this is how we do it in TensorFlow. Naive base 50%, Unigram binary 89%, and Bigram binary 90.4, and Bigram TF-IDF 89.8. So it is better than Unigram simply because the Bigram part was better, but it is worse than the Bigram binary simply because the TF-IDF did not work here. Again, typically this TF-IDF for text classification is going to increase the performance by 1%. All right, now let's do the sequence modeling approach. So remember, we started with the bag of words, right? And in the bag of words, we manually engineered some features. What was that? So for example, we said that clearly using bigram tokenization was better than unigram tokenization, right? So we're doing some kind of feature engineering, and it seems that the ordering was kind of important in the previous example because unigram encoding was doing a worse performance compared to bigram. Now we want to automate all this engineering, right? So and after all, this is the whole point of deep learning, right? We want to move away from that manual feature engineering toward letting the model learn their own features from being exposed to the data alone, right? So this means that instead of manually crafting those order-based features, we're going to expose the model to raw data, to raw word sequence, and let it figure it out what those features should be, right? So this is what the sequence modeling is all about. So here are the steps. We're going to start by representing the input as a sequence of integers, and again the key term is sequence. This is a sequence of integers now, and it of course one integer for each word, and then we're going to map each of these integers to a vector to get the sequence of vectors. Now we have a sequence of vectors, right? And we can go ahead and one-hot encode that vectors or use word embedding. I'm going to do both ways and see which one performs better. Then now that we have an input, we're going to feed these vectors into a stack of layers that are able to handle, are designed for sequence modeling, like the layers that can preserve the order more specifically. So what are those layers? It can be a 1D convolutional neural network layer, it can be RNN, LSTM, or transformers, right? Okay, now let's see how this text vectorization layer is doing the job. So again, the max token is 20,000. This is our vocabulary size. And now we have this new thing, it's called max length. So basically this is the maximum number of words that we're going to see in each review, right? And we choose the 600 because the average word length for each review was 233 in this data set, and only 5% of the data go beyond 600 words, right? So at the end of the day, and we're going to, of course, the output mode is going to be integer. Remember, we want to come up with this sequence of these integers. and then the length of that integer can be equal to 600, right? So now we can do one-hot encoding or word embedding, right? So for example, if you do one-hot encoding, we're going to end up with something like this. So we will see, let's say each word has, this is dimension 20,000, right? We have 20K, and we have 600 of these words, right? So 600 of these words, this is one-hot encoding representation, right? So this is our 600 words, and each one is a vector of, let's say, dimension 20,000. So as you can see, there's lots of multiplication going on here between 0, 1. So right away, 600 multiplied 20,000. So this is going to be a large number, right? So this is our basically 12 million float. So 12 million float. So as you can guess, if I do one-hot encoding, it's going to be it's going to be slow because of this large number of float calculations for just one single review, right? So however, let's do that. Let's see how it performs and if we can do better. Okay. We're going to start with one-hot encoding. So there you go. This is our one-hot encoding approach. Basically, we're going to encode integers into binary 20,000 dimensional vectors. So this is the one that I showed you in the previous slide, right? So let me see. No, that's going to be our input, and we're going to add this embedding layer by just doing one-hot encoding, again 20,000 dimension. And then now, because we want to keep track of the orders, we have to come up with sequential modeling, right? So we can do, for example, LSTM, RNN, or here we're doing the bidirectional LSTM with 32 nodes, right? And we can do dropout, we can do recurrent dropout if you want, and then finally the output layer is going to be our regular dense layer with one node, activation sigmoid, and the rest is pretty straightforward, right? We're going to review these things in the Python part as well. And so in terms of performance, naive base was 50%. We get it up to 90.4 with Bigram binary. However, with using sequential modeling, one-hot encoding, it's only 87%. So if anything, it's even worse than the Unigram binary. And the model was trained so slowly. So this means that there must be a better way. There must be a better way than one-hot encoding, and that's basically what we're going to cover in the next slide, which is word embedding. All right, now let's see how we can improve the sequence modeling approach by doing word embedding. Remember, one-hot encoding was too slow. Let's see if we can do better. There are two different ways that we can incorporate word embedding. The first one is simultaneously train those word embeddings with the neural network's weight. So it's going to happen jointly, right? So once the model is doing backpropagation through time and calculate the weights of the neural network, it's going to figure out what are the word embeddings as well. So that's one way. The other way is use pre-trained word embedding. So just like what we covered in computer vision and transfer learning, it's the same idea. So if you think that, okay, a text is a text, I can use word embedding, which has been driven from some pre-trained model. Let's go ahead and do that. However, you have to be careful. Sometimes the context is different, right? So sometimes we need to learn those new embeddings from our own specific data. Imagine you are dealing with a legal document classification problem. And if you use a pre-trained word embedding that was trained on a movie review, maybe this is not the best idea, right? So maybe for legal document classification, you should go ahead and use the first approach. Simultaneously, find those word embeddings learn those word embeddings from the data. And obviously, it comes with a caveat that it's going to be, of course, more computationally expensive. And then, so here's the process. We are going to make sure that we get the word index. This is going to be high dimensional. We apply the word embedding layer, and the output is going to be corresponding word vector, which is lower dimensional. So again, this is our embedding layer. We are going to go from the size of 20,000 to, in this example, 256. So basically, we are taking these vectors that were 20,000 and transforming them to a corresponding word vector, which here we said 256. It's, of course, it's a lot lower dimensional. For each word, we're going to use one of them, and then here we're going to have 600 words, so we're going to concatenate 600 words of these things together. Okay, then we're going to apply our regular bidirectional LSTM with 32 nodes. add a dropout layer, and then this is finally our output layer. Let's see what is the performance. Okay, here is the performance output. So it seems that let me actually show you one thing before I get to that. This is maybe this is going to help you understand it better. So we have 600 words in this example. The dimension is 20,000. Use word embedding to reduce it to 256, but we're going to use it for the same 600 words, right? So this is a review, the max length of the review, right? And so again, the naive baseline was 50%. This is our best performance, Bigram binary. And now with our sequence modeling, so these are the sequence modeling approach. The one-hot encoding can get us 87% accuracy in the test set. For word embedding, we did actually two models. Again, don't worry, I'm going to cover these things in the Python sections. But we did two models. One we were using the masks, the other one with no mask. So let me tell you what do I mean. Either way, it didn't improve that much. We get to 87% and 88%. And there are a couple of reasons for that. So one reason is that we said that, okay, the max number of words in a review that you use was 600. So maybe this truncation of the data is not helping us that much. That's number one. And number two is that this data set was large enough, and the representation that we could learn using a simple Bigram binary was enough, at least for this case. So we didn't need to do word embedding, or we didn't, even if we do pre-trained word embedding, it didn't help that much for this example. Now let's see what is the difference between this one and this one. Okay, the one with a mask, the one without mask. Okay, remember we are using bidirectional LSTM, so it means that when we are going through the word vectors, we go from left to right and then right to left, or you can think of it as bottom to top, top to bottom, right? So here, if we don't use mask, so here mask is equal to false, it means that imagine you have a review, and the review is something like this. The movie was good. How many words do we have? 1, 2, 3, 4. However, we are using 600 for here. So it means that there's going to be, maybe the first 4 of them has some numbers, and the rest is all 0, right? So these are all zeros. So this all zeros were added by paddings where we were indexing, right? And the idea is that, so basically padding means that we just use 0 to make sure that we can have the same length for all the inputs, right? But those paddings will mess the internal states in RNN, especially when we're doing bidirectional RNN, right? So we need to tell RNN that to just skip these paddings, skip these iterations, right? So this is called masking. So if I skip those iterations, basically it's going to put a flag true or false. Okay, this is padding, flag true, just ignore them. So this is what masks is equal to true is doing, right? So especially again for bidirectional, it's going to be a big deal. And here we improved it from 87% to 88%. But overall, it seems that our simple bag of word approach was a better one compared to sequence modeling approach. Again, so it seems that in this IMDB review sentiment classification, the local ordering was more important than let's say, the global ordering of the review. And this is actually what we get by comparing the performance of the model between bag of words versus sequence modeling approach. All right, I'm going to wrap up this section by briefly talking about pre-trained word embedding. So the motivation should be clear. When we have little training data set, so this means that the network cannot learn those embeddings from the data itself, right? So that's why we're going to go ahead and leverage from those pre-trained word embeddings. This is pretty much analogous to where we used the pre-trained convnets in image classification. We said that, okay, after all, if you have a data set that has been trained on millions of images, the image is image, the corner is corner, the edge is edge, so these are all the same. So we can extract those features and apply to our own model. The same story here. We're going to use the word embeddings that have been pre-trained on a huge, large corpus of data, and then we're going to transform our input based on those word embedding and generate a lower dimensional input and pass it to our neural networks. So that's how the pre-trained word embedding is going to help us. Okay, so, and just be aware, I already talked about it, this is useful when you're expecting generic features, right? So if this is a special topic, for example, legal documentation classification, that's going to be the terminology, everything is going to be different there. So probably you have to, if there's a pre-trained model with that context, awesome, go ahead and use that. If not, you have to make sure that you train your own word embedding simultaneously with the neural network weights. Okay, so there are different schemes. There are many schemes actually out there, but the two more successful ones, well, the ones that have worked in practice, is one which was developed by Google 2013. It's called Word2Vec. This is one algorithm. The other one is GloVe, which was developed 1 year after that in 2014. So again, there are many of them out there. These two are already built in well, not built in. We can use them with TensorFlow. Actually, I'm going to show it to you in the Python section, so don't worry about it. But at a very high level, the Word2Vector is a predictive model. It uses a neural network. It's a separate neural network for making these predictions to predict the probability of a word given its context. The GloVe is a counts-based model, so basically it's compute the co-occurrence probability between words in a corpus. And yep, so just remember in terms of the difference, both of them works very well in practice, especially if your task is very generic and it simply should work. But Word2Vec is faster to train than GloVe, especially for larger corpora. Okay, so that was it. This was our NLP, and let's actually conclude this section. All right, we are done with the theory part of our module number 6. In the next couple of videos, I will cover the application of these deep sequence models in Python. And after that, we are going to go to the state-of-the-art models, namely transformers. Until the next one, take care.